So, welcome everyone. Really happy to see you here. This is the first time I'm giving this presentation. My name is Adam, and I've been a developer since '97. And I've been interested in programming long before that, and I still enjoy it, and I still try to improve a little bit. And yet it took me quite some time to understand that the main challenges in programming is not so much about writing code. Because we programmers, we're actually quite good at that. A much larger problem is to understand the existing code. And I've been thinking a lot about that over the last couple of years. How should we express our code to make it fit the way our brain wants it? To make it easier to reason about and to think about it and to evolve it. So, this is about that. But why beauty then? Because beauty is fundamental to the way we work as humans. And you can see that all the time. But most of the time, we're not consciously aware of that. And just to give you one example, when you meet an attractive person, you immediately consider that person to be not only more friendly and more social, but also more intelligent and more competent based on appearance alone. And of course, the word isn't fair, but I mean, it's a good thing for us here, right? And beauty goes deeper than that. There's been some studies on juries during trials, and it turns out that the offenders, the more attractive they are, the weaker the punishment they get. So, beauty affects us on many levels, and we're not always aware of that. And this is true in code as well. But before we discuss that, we need to arrive at a shared definition of beauty. I want to arrive at an objective definition of it. And before we go that, how many of you have seen my other presentation, Code That Fits Your Brain? A few people. Okay, that's great. Your task is to pretend that you're surprised now. And the rest of us will arrive at the definition of beauty by doing a psychological experiment. Are you ready? All right. So what will happen is that I will show you some pictures here. Pictures of faces. And your task is to identify the face that you find the most attractive. All right, let's go. Just pick the face you find the most attractive. So, if you're like the majority of people, you pick the woman here in the upper left corner. Let me see a show of hands. How many picked that woman? I think it's a majority, but the bad news for all of you that picked that woman is that if you hope that you someday meet her, the bad news are she doesn't exist, and she never has. This picture is a composite of all the other pictures. And those pictures are from a very famous psychology study performed in the early 90s. And what researchers found out was that as they started to take photos of individual faces and morph them together, the more photos they combined, the more beautiful the end result, or the more attractive. And this is a little bit surprising, because what happens is, when you start to combine photos, you remove individual differences. And the end result actually goes towards an average. So that means that beauty is nothing more than average, right? And for us, that means that our average code base, that must be beautiful code, right? I don't think anyone agrees with me, so I don't even agree with myself here. So clearly, we're missing something in our definition. So let's have another go at this. It turns out that beauty is indeed average, but not average in the sense of common or typical. Beauty is average in the sense of, in a mathematical sense, because that's what's happening. Have a look at these faces here. Those are taken from another, or more modern study. And they're made up, I think, of like 20 individual photos, each one of them. And you see all those individual differences have been erased. You have very symmetrical, mathematically pure faces there. And we humans seem to be attracted to that. But beauty as an average also means that beauty is not so much defined by what's there. Beauty is more about what's absent. Because beauty is the absence of ugliness. right? And that gives us a definition to work with. With the absence of ugliness, beauty is actually a negative concept. So, why is this important for programmers? Because we can reason in the same way about code. Beautiful code is code without ugliness. And ugly constructs in programming, that is everything that puts an unnecessary load on our brain. Right? Things like complicated, explicit conditional logic, explicit loops. When we talk about architectures, we have things like inconsistent error handling or multiple ways to communicate between different subsystems without any good reasons. That's ugliness, and it's terribly expensive. And that's why I think that beauty matters. And what I want to do today is to present a set of case studies for you. The first one is going to be quite specific in order to really reason about this. And after that, we're going for a bit of a wilder ride. And my goal today is that all of you, I want to provide you all with at least one little new idea. So please let me know afterwards how it turned out. I'd be really happy to learn. So our first study is about a language feature called named arguments. And it's a pretty common feature. You see it in Python, for example. Python programmers use named arguments all the time. You have it in C#. And this is an example of a C# function. We have the function fire, and it takes two arguments, a location and a weapon, right? And we can invoke this function in 3 different ways. First of all, we can invoke the function giving the arguments in a positional manner, the normal way to call a function, right? Since we have support for named arguments, we can also put names on the arguments. And the names we use correspond to the names in the function definition, right? And since we're naming our arguments, we can also switch the order. And this is actually quite important because it gives us an opportunity to optimize for readability in a local context. We can choose the order that communicates the most. So, named arguments is a quite common language feature. I was fortunate enough to start quite early with Clojure, the programming language. So let's have a look how named arguments could look in Clojure. Here's our C# function that we saw before, and if we translate this to Clojure, it looks like this. All right, so in Clojure, it's a Lisp, so we wrap everything in these beautiful parentheses, and we use defn to define our named function, fire, and then we just name our arguments, right? It's pretty straightforward. And in Clojure, we invoke the function like this. It's almost exactly the same, the name of the function and then the positional arguments. And back when I started, say 5 years ago, is anyone programming in Clojure? Yeah, you do, Thomas. So 5 years ago, if you wanted to do named arguments in Clojure, there was no way to do that. And that was a bit of a surprise to me because Clojure, from a language perspective, it's really on the bleeding edge. It has a lot of really cool stuff in it, but named arguments was missing. And I wasn't the only one that thought that named arguments were missing. So a bunch of programmers got together and developed a library, which included a new function, defnk. Because this is the cool thing with Clojure. Since Clojure is a Lisp, it means that the code, your source code, is actually data. And that means that you can manipulate your own source code just the way that you would manipulate any other data structures. And that gives you, as programmers, the power of a language designer. So, in case you miss some feature, you can implement it yourself. And that's pretty cool. And that's what they did with defnk, which allowed for named arguments. And the next thing that happened was that these programmers tried to convince Rich Hickey, the inventor of Clojure, to incorporate this defnk function in the core language. But Rich Hickey, he didn't like that. He said, "Oh, right, let me think about this for a while, and I'll get back to you." And what Rich Hickey did was that he took one of the most elegant design decisions I ever heard about. And I would like to share that with you here. So, what Rich Hickey did in Clojure was that he decided to implement named arguments in a radically different way. on top of a language feature called destructuring. And destructuring is something you find in a bunch of functional programming languages. And I will try to explain that to you by using a pseudo C# version. So if C# had destructuring, it could have looked somewhat like this. All right, we define a dictionary, and we just include key value pairs in that dictionary. Pretty straightforward. Now, what destructuring does is it's basically a compact way to pull things out of a data structure. And what you do is that you declare a destructuring pattern. In this case, we want to extract all values that are associated with the following keys. So this is our destructuring pattern, and here's the dictionary that we want to extract it from. And what destructuring does now is that it picks out all values that corresponds to the keys and introduce variables for them, right? So after this single line of code, I can do the following. I can print out all values. So it's a very compact way to pull things out of a data structure, right? And destructuring is a feature that was actually present in Clojure from the very start. Here's how it looks there. In Clojure, you define a dictionary by using these curly braces, and then it's exactly the same principle, key value pairs all the way. And the destructuring pattern in Clojure, since Clojure is a dynamically typed language, so we need to tell it here, all right, it's about keys that we want to pull out of a dictionary, and then we just write our keys here and the dictionary. And the language will make sure that the dictionary is destructed, and these symbols are assigned the values we want, right? It's exactly the same as in the C# pseudocode I showed you earlier. Now, look here what happened. We started out here. This is the Clojure function where we started, defn fire, and we can call it like that, only positional argument supported. What Richike did now was that he extended the support for destructuring to function argument lists. And the important thing here is that it's exactly the same pattern that we use in function arguments list as we were used to earlier. So now, with this small change, I think it was actually a one-line commit. We can support named arguments in Clojure by using key value pairs, and the language will wrap that up in a dictionary, throw it at the function, which uses destructuring to pull it apart. So that's the design decision he made. And to me, the beauty of this is that, first of all, we could get rid of a special case because we don't need defn k anymore. Now we just have one way to define functions in Clojure, right? And that's a big win, to get rid of a special case. But even more important is the fact that as Clojure programmers, we didn't have to learn any new concept. We could take all that knowledge we had about destructuring and apply it in a new context, apply it to function arguments list. And to me, Richike's design decisions point at a much broader principle. And I'm pretty convinced that to extend an existing concept is always more attractive than to introduce a special case, right? So let's look at something completely different. Get a bit of a relief from the Clojure stuff. Let's talk about culture. I think that we programmers, we actually talk quite a lot about cultures. But we talk about team culture or a company culture, something like that. What we rarely talk about is how all those cultures affect the kind of code we write. And this is important because beauty has a large cultural component as well. And everything I told you before, you know, when we did a psychological experiment, beauty as a mathematical average, as the absence of beauty, all that is true universally across all cultures on Earth. So no matter where you go, those are things that people will value, find attractive. The things that tend to worry in a psychological perspective is those things that we actually can change. I mean, there's no way for me to make my face more mathematical average, but I can, if I choose to, I can become larger or I can become thinner, right? so those things are the things that tend to be the cultural component. And you can see that here. This is Venus from Willendorf, a pretty famous statue that shows a 20,000 years old beauty ideal. And you don't have to go 20,000 years back. Just pick up a fashion magazine that's 20 or 30 years old, and you will see how the male bodies and the female bodies have changed over the course of time. And we have a large cultural component in programming as well. And this became apparent to me because I've recently started to become interested in a language family called array languages. Array languages are things like APL, K, J. You see, they are really creative with the naming. So let me ask you here, does anyone know J, the programming language? You do? Perfect, then you can check my code here. That's excellent. All right, so what I do when I learn a new language is that I pick up some existing code and have a look at it, because I want to find out what can I expect when I start to do this? What kind of values do the community have? Those kind of stuff. So I look at a lot of existing code. And I did the same thing as I started to learn J. I went to reset the code and looked at some solutions to some interesting problems. And one that I kind of liked is this one. The task here is to take the language name, J, and print it in ASCII graphics in 3D. And that's actually, it's not that trivial. And here's how it looks. I found a few J solutions. This is one of them. You see the J logo here? It's a bit rotated. And there was another solution as well. And actually I like that. I like the retro feeling there. It's pretty cool. So now, your task. Think of your favorite programming language. The language you are most productive in. How many lines of code would you need to produce those pictures? And I know that these days, it's all about no estimates, but anyway, please give me a number. Come on, 500, 1,000, 100, more, less? Anyone? 1,000? Excellent. Will you be done by Friday? No, sorry. 1,000? Anyone, more or less?
You mean given an arbitrary text or just...
No, just a J. Let's limit us to this J. I think 1,000 is pretty good, right? So, let me tell you this about J. This is what fascinated me with the language. It has an extremely compact representation. So this solution here is done with just 36. That's pretty impressive, right? 36. And I don't mean lines, I mean characters. Here's how the code looks. I know it's pretty dense. The first time you see that, it's almost, you know, like a comic book, a censored cursing character. But, okay, I won't pretend that I understand everything about it. But when you start to learn J, you appreciate the beauty of it. Because behind this cryptic syntax, there's a lot of beauty. J is pretty much absent of special cases, and it has a lot of consistency in the way that it represents things. So I think that J is actually a much simpler language than Java. We're just not used to it. And let me tell you another thing about this. Sorry. There, let's stop there, right. So, the fascinating thing about this, have a look at it and think about what's absent. I mean, I spend most of my time programming .NET, C# these days. And in C#, and I'm pretty sure it's for the majority of languages, we value expressive and long and clear variable names, right? You won't find that in J, because to a J programmer, those long descriptive names are just noise. They think that those names would distract the programmer from reasoning about the stuff that really matters, the stuff that actually does something. And that's pretty cool, because another thing about J is that it's not meant to be read like this. most of the time when you try to understand J, you play around with it interactively. You break it apart, take some small parts and try it out with some sample data. And when you understand that, you pick the next part and you build up your knowledge incrementally. And that's quite a different way. And that's the kind of way your thinking starts to change when you suddenly can see your whole program on one single line of code instead of spreading it apart in multiple files and classes. But when I saw that, I started to think about the pretty famous psychological principle that's called the mere exposure effect. And the mere exposure, it just means that we tend to like the objects and things that we see the most. And it's pretty easy to see the evolutionary advantage. I mean, think back to the Stone Age or whatever. We lived in our pretty small communities, and the people around us and the things around us, they were probably quite important for our survival, right? So it made sense to kind of fancy and like those things we saw on an everyday basis. So that's the mere exposure effect. But what surprised me with it is how strong this effect is. There's been a fascinating experiment when you present people with some kind of stimuli. Say they test, for example, in one of the tests, they used Chinese characters, right? So you were presented with 2 Chinese characters, and you had to choose one of them, the one you liked the most, the one you found the most beautiful. Now, the twist was that just before they showed you these choices, they flashed one of the images really, really fast, 150 milliseconds, which is below the threshold that we should be consciously aware of it, so we don't know that we've seen anything, but fast enough that we should be unconsciously aware of it. And those 150 milliseconds were enough to bias our choice. We preferred the picture that we have seen really fast. So now, please think about this. If 150 milliseconds is enough to influence our sense of beauty, what do you think happened when we spend 8 hours a day looking at the same kind of code all day, all week long? So, I think that in order to arrive at true beauty, we need to separate those 2 things. We need to separate our cultural values from the genuine beauty we have. And we must take care to not confuse our sense of familiarity with beauty. And the only way to do that is to look across languages and paradigms. So, as I started to study psychology, I mean, it's a terrible experience, because as soon as you start with that, you notice how flawed we as human beings are. It's a wonder that we work at all, that we function at all. And particularly when I start to study cognitive psychology, I soon realized that this programming stuff, it should actually be much too hard for us. And still we do it every day. Somehow we manage to overcome our limitations. And we do that by providing workarounds, and those workarounds are actually quite efficient. So let me tell you about that by giving you a little story. This photo, by the way, it's not a composite picture. This is Alexander Luria, a very famous Russian psychologist. He's not as well known as Sigmund Freud, but I think Luria's case studies are actually much better. At least they are a bit more scientific than what Freud had. Anyway, one of my favorite case studies from Luria is about a memory specialist. This memory specialist, he had a picture-perfect memory. And Luria followed him through several decades. And what this guy did was that he used to go from town to town and entertain the crowds at markets. So he did something like I do. He stood in front of a crowd, and then he asked everyone, please give me a number. And people started to shout random numbers at him. 107, 13, 98. And behind him, his back, another guy was standing and wrote down each number. Now, as soon as that, I don't know what he used, but as soon as that was filled, the memory artist repeated all those numbers in order, of course. And if you asked him, he could do it backwards as well, or from right to left. It really didn't matter. And that's quite impressive, right? But let me tell you this. I can promise you that each one of you could learn that trick. It's just about trying hard enough and practicing enough, and there are techniques for that. So it's hard, but it's doable. But the next thing that happened isn't doable for a normal person. Because Luria was there, and he wrote down all those digits and preserved them. And then he tested the memory artist much, much later. In one case, 10 years after the event. So he went to him and said something like this. Can you remember that time when we were at the market in Irkutsk? Yeah, sure, I remember. That was the numbers 107, 13, 98. He could remember every single digit here he has ever heard over the period of a decade. That's quite impressive, right? So I started to think, what would happen if this guy chose a programming career? What would be different? And first of all, descriptive variable names. Completely uninteresting, right? Because he can remember why he has every variable there. So he could choose single letters names without a problem. What else? Immutability, encapsulating side effects. Completely uninteresting. He can remember the order of everything. Doesn't really matter. But I can promise you this. That guy would be a terrible programmer. Because it's easy to be blinded by all his gifts, his perfect memory, and easy to miss the disadvantages that has. Because he never learned to abstract. Since he had a perfect memory and he used to visualize everything, he never needed to learn that workaround we call abstraction. And as a consequence, he had terrible problems to reason about abstract concepts. Like, for example, take the concept of nothing. How do you visualize nothing? I don't know, and he didn't know. So I think he would make a really bad programmer because he never learned to abstract, and he had no way to learn that. But we are usually quite good with abstractions, right? And I think that's one of our key strengths, and I think we can take it one step further. And here's a small example of that. Again, this is some C# code, and we have two methods here. List RSS that takes a language ID, news item that takes a news item ID. All right, that's pretty simple, and the variable names are pretty clear and expressive. But have a look at the types. An int, a news item is also an int. Are they really the same type? Is a language ID the same thing as a news item ID? I don't think they are. So what I do when I see this kind of code, and I'm pretty sure most of you do as well, is that I introduce simple domain types. So I go from integers to a language, and the other one becomes a news item. And this is pretty basic, but it makes a huge difference in terms of readability, because now, as I start to express my domain with the type system, the variable names are free to express the context. And that way, I can communicate much more information in a single line of code. So that's my next recommendation, to always put our domain in a context. We're used to think about static type systems as a way to do compile time checks or perhaps for performance reason, but to me the main value of a type system is the communication it enables. All right, I've arrived at my last case study here, and this one is about architectural beauty, because everything I told you so far about beauty applies on an architectural level as well. It's just that much more important, because the consequence of breaking beauty, the consequence of ugliness, is so much more severe on an architectural level, right? And I would say that we programmers, we're actually pretty good at software architecture. We usually have a pretty good idea about what we want the system to do and how it should look. I think the mistake we make, and I don't say that this is universal, it's just something I've seen quite often, is that we fail to reason about how the system shall evolve. So it's quite rare that we reason about our systems. How do we look in a period of time, say 1 year from now or 5 years from now? In what direction do we want them to evolve? And the risk with that, if we miss that part, is that we end up with something like this, where the system doesn't support the kind of changes we want to make to it. We get conflicting changes in the same modules by multiple programmers, which in turn is a problem because that's one of the best predictors of post-release defects. How many programmers that co-wrote a single module. And we also risk getting unexpected feature interactions, and the system gets terribly hard to reason about. And to somehow solve these problems, I think we need to take a step back and consider what software architecture is actually about. And to me, software architecture, and I'm pretty sure you agree, it's not just a blueprint, right? I think we need diagrams, we need visualizations, but to me, a software architecture is a number of bold principles, bold decisions. And those principles they could be things like the error handling policy, or how things should communicate with each other, or how we are expected to work with the system. I think those principles are the most important thing because they guide the system, they constrain it a bit, and it's something that can live along with the system and help it evolve in a successful direction. And I try to base my principles on patterns. I'm a big fan of architectural patterns because a pattern, as we all know, it's not just a solution. It's a solution with a context. And the thing I like most about patterns is that they list all the trade-offs. So I know the consequences of applying this particular pattern in my context. And when I choose to do that, it's because I expect a positive outcome, right? I expect some positive benefits from applying my pattern. And that's good, because it gives us a way to reason about beauty. Because what's ugliness in that context? I would say it's everything that breaks our principle, that breaks our patterns. Because if we start to do that, we can't expect the positive outcomes, right? So, over the past years, I spent a lot of time trying to measure this stuff. And I want to tell you a bit about that. This is a case study I did of a fairly large e-commerce site. 500,000 lines of code, most of it C#. I think it's like 100,000 lines of JavaScript and 50,000 lines of SQL. So it's a mixed environment. It's pretty big. And as you see, this is the main architecture. It's based on View Controller, MVC. And MVC, like most other patterns, it looks a little bit different in each context. And in this case, they did quite a typical variation. They introduced some additional layers. And this is quite common. You have a service layer, you have a data access layer, perhaps you have a repository beneath that, and an object relationship mapper, and so on. I mean, it's not uncommon with 7 or 8 or even 10 layers stacked on top of each other. And there's a reason we do this layering. I think the main reason is the separation of concerns. It's about encapsulating responsibilities in each layer, right? So that may be one architectural principle in this system. And that means we can start to reason about beauty. We can start to reason about ugliness. Because what would be ugly in a system like that, with that architectural principle? If our purpose is to encapsulate responsibilities, I would say that ugliness, that's changes that go cross through each layer, right? That runs contrary to the purpose we have with it. Something like this. So I start to look at the system to find out how many of the changes we make that actually take this direction, that go through multiple layers. And that's the kind of data that we actually have on every project. We're just not used to work with it that way. the way we work is recorded in our version control system. So what I did here, I mean, this project had literally thousands of commits. So I wrote some programs that just went through the commits and analyzed each change and looked at each commit to deduce which layers it affected. And then I collected that statistics, and here's how that looks. So first we have the MVC parts. We have the models, and it turns out that the models were changed in 75% of all commits together with the views. That's pretty high number, right? 75% of all commits, and you have to change both the models and the views. In 68% of the cases, we had to change the models and the controllers together, and 66% of the cases, the controllers and the views. So this basically means that in 2/3 of all the commits we make, we have to change the whole MVC part, each individual component. That gets expensive pretty fast. But it gets a bit worse, because it turns out these models, views, and controllers, they have a dependency upon a package called core, which is kind of a utility package. And it turns out that in 50% of all commits, those change together as well. Right? And we also see that the MVC parts changes together with the services layer in approximately 35% of all cases. So this means, yeah, when I see something like this, it worries me, because such a system gets quite expensive to work with. If every third change I do affects every single layer in the system, well, perhaps we have separated the concerns, but I'm not sure they were the right concerns. And all this is data that you already have. And let me show you a final example. Those kind of analyses, they're of course not limited to model view controller. You could do exactly the same thing with other architectures. For example, here's a sketch of a service-oriented architecture. And if we apply the same reasoning principle and start to reason about individual services, the important thing there is, of course, to encapsulate responsibilities in a service. We want to be able to replace services and vary them independently. So ugliness in that architecture would be changes like this that go through multiple services. And that's what I would look for in those kind of architectures. So would be really happy to talk more about that later. Let me just sum up. What I tried to explain to you now was that I think this is actually one of the most important things we can do to ensure that our architecture actually fits the way we work with the system and the way we as people are organized, because it really makes a huge difference. So let me sum this up for you. First, we start to look at closure and named arguments, and we found a general design principle that to extend an existing concept is always a more attractive solution than to introduce a special case. We then looked at culture and discussed the importance of separating what we're familiar with from true beauty. Finally, we talked about putting our domain in context before we wrapped it up with an architectural principle to ensure that the architecture support the kind of changes we make to a system. I think that takes us a step closer to arriving at beauty in our architectures too. So that was everything I wanted to say now. I will be very happy to discuss it afterwards, and thank you very much for listening. Thanks.